Have you ever wondered how aircraft manufacturers ensure every critical component is completely safe before a plane takes off? Or how automotive engineers detect invisible cracks that could lead to catastrophic failures? The answer lies in a fascinating technology called magnetic particle inspection. Welcome back to the channel. Today, we are diving deep into one of the most widely used non-destructive testing methods in industries ranging from aerospace to oil and gas. By the end of this video, you'll understand exactly how magnetism helps us see the invisible flaws that could save lives. Don't forget to hit that subscribe button and turn on notifications, because we're about to make NDT exciting. So what exactly is magnetic particle inspection, or MPI? MPI is a non-destructive testing method used for defect detection that uses magnetic fields and small magnetic particles to detect flaws in components. The beauty of this method is that it's fast, relatively easy to apply, and doesn't require extensive surface preparation like some other NDT techniques. This makes it particularly effective at detecting surface and slightly subsurface discontinuities. But here's the catch: the component being inspected must be made of a ferromagnetic material such as iron, nickel, cobalt, or some of their alloys. If your material can't be magnetized, this method won't work. Think of it as a combination of two inspection techniques: magnetic flux leakage testing and visual inspection. When we magnetize a part and it has a crack or defect, that defect disrupts the magnetic field, and tiny iron particles help us see exactly where the problem is. To really understand how MPI works, we need to talk about magnetism for just a moment. Don't worry, I'll keep it simple. Imagine a simple bar magnet. It has magnetic lines of force running through it and around it. These lines exit at what we call the North Pole and enter at the South Pole. Now, here's where it gets interesting. If you break that bar magnet in the center, you don't lose the magnetism. Instead, you create two complete magnets with poles on each end of each piece. And if the magnet is just cracked but not completely broken, a north and south pole will form at each edge of that crack. This is the fundamental principle behind MPI. When we magnetize a component and there's a defect like a crack, void, or inclusion, it acts just like breaking our bar magnet. The magnetic field is forced to exit and re-enter at the defect, creating what we call a flux leakage field. When iron particles are sprinkled on a cracked magnet, they're attracted to and cluster not only at the poles at the ends, but also at the poles at the edges of the crack. This cluster is much easier to see than the actual crack itself. So what kinds of defects can MPI actually find? This method is incredibly versatile. MPI excels at detecting surface breaking cracks. These are your fatigue cracks, grinding cracks, quench cracks, and weld cracks. But it doesn't stop there. MPI can also identify near-surface discontinuities, meaning defects that are slightly below the surface. Common defects include porosity in castings, cone laps and shrinkage cracks, lack of fusion in welds, seams and inclusions, forging laps and bursts. The method is particularly sensitive to linear defects that run perpendicular to the magnetic field. This is important because we'll need to adjust our magnetization technique based on what we're looking for. You might be wondering who actually uses this technology? The answer is almost every major industry you can think of. Industries using magnetic particle inspection include structural steel, automotive, petrochemical, power generation, and aerospace. In aerospace, MPI is critical for inspecting landing gear, engine components, and structural elements. One small undetected crack could be catastrophic. The automotive industry uses it extensively on crankshafts, connecting rods, and chassis components. Power generation facilities rely on MPI for turbine blades and pressure vessels. And here's something fascinating: underwater inspection is another area where magnetic particle inspection may be used to test items such as offshore structures and underwater pipelines. Non-destructive evaluation. Yes, this method can even work underwater. The railway industry uses it for rail inspection, the construction industry for structural welds, and manufacturing for quality control of machined parts. If it's ferromagnetic and failure could be dangerous or costly, there's a good chance MPI is being used to inspect it. Now let's talk about the tools of the trade. What equipment do we actually need to perform magnetic particle inspection? First, we need a magnetization source. This can range from small portable electromagnetic yokes that technicians can carry by hand, all the way up to large custom-built stationary units for production line inspections. The choice depends on the size of the part and where you are doing the inspection. Next, we need the magnetic particles themselves. These particles are made from precipitated soft iron and are stained or dyed in various colors, usually with fluorescent dye or red dye. Here's the difference. Fluorescent dyes on particles in a liquid suspension are used to find very tight surface flaws, while visible dyes on dry particles are less sensitive to tiny surface defects but better for finding subsurface flaws. If you are using fluorescent particles, you'll need ultraviolet lights. These particles fluoresce at 365 nanometers, requiring proper UV intensity at the surface for inspection. Inspectors often wear special UV goggles that filter the ultraviolet light and amplify the visible green and yellow glow from the fluorescing particles. You'll also need proper lighting, cleaning equipment, the magnetization equipment, and depending on the method, either a carrier liquid for wet particles or air applicators for dry powder. There are two main techniques for applying magnetic particles: dry and wet methods. Each has its own advantages and specific use cases. The dry method uses fine iron powder particles that are dusted onto the surface while the part is magnetized. This method is excellent for detecting subsurface defects and works well on rough surfaces or in field conditions. It's also great for inspecting large, irregular components like castings and forgings. The wet method, on the other hand, uses particles suspended in a liquid carrier, either water or oil-based. The magnetic particle suspension is carefully sprayed on or poured onto the component or specimen. This method provides better sensitivity for detecting very fine surface cracks because the liquid helps the particles move and settle into tight defects. Wet system particles often have pigments applied that fluoresce under ultraviolet light, making even the smallest defects glow brilliantly in a darkroom setting. This is why you'll often see inspectors working in dark booths with UV lights there, using the wet fluorescent method for maximum sensitivity. The choice between dry and wet depends on your specific application, the type of defect you are looking for, and your working environment. Alright, let's walk through the actual inspection process step by step. This is where theory meets practice. Step 1. Surface preparation. Before anything else, the surface must be cleaned. Remove any dirt, oil, grease, paint, scale, or loose rust. The surface doesn't need to be polished, but it must be clean enough that particles can move freely and settle into defects. Paint thicker than about 0.005 inches must be removed. Step 2. Magnetization. The first step in magnetic particle inspection is to magnetize the component that is to be inspected. Non-destructive evaluation. This can be done using direct current, alternating current, or permanent magnets. The type of current matters. Alternating current is commonly used to detect surface discontinuities, while full-wave DC is used to detect subsurface discontinuities. The magnetization must be oriented correctly. Remember, defects perpendicular to the magnetic field show up best. This often means we need to magnetize the part in two directions to catch all possible defect orientations. Step 3. Application of magnetic particles. While the part is magnetized, and this timing is crucial, we apply the magnetic particles. After the component has been magnetized, iron particles, either in dry or wet suspended form, are applied to the surface. Step 4. Inspection. Here's where the magic happens. If the current encounters a defect, the magnetic field will be interrupted and spread out from the point of the defect, creating a flux leakage field. Particles are then drawn to the leakage field. Under proper lighting, whether visible light for dry particles or UV light for fluorescent particles, the inspector looks for particle accumulations that indicate defects. These patterns are evaluated against acceptance standards. Step 5. Demagnetization. After inspection, the test object often needs to be demagnetized to remove residual magnetism. This prevents issues with subsequent machining operations or interference with sensitive equipment. So why choose magnetic particle inspection over other NDT methods? Let me break down the major advantages. Speed and efficiency. MPI is fast and relatively easy to apply, making it perfect for high-volume production environments or time-sensitive projects. Cost-effective. Compared to some other NDT methods, MT is relatively low cost. The equipment is affordable, and the consumables are inexpensive. Minimal surface preparation. Part surface preparation is not as critical as it is for some other NDT methods. You don't need a mirror finish, just a clean surface. Versatility: MT can be used on a variety of ferromagnetic materials, including iron, nickel, cobalt, and their alloys. It works on complex shapes, rough surfaces, and even on items with coatings. High sensitivity: the method can detect extremely fine surface cracks that might be invisible to the naked eye. With fluorescent particles under UV light, we're talking about cracks that are mere micrometers wide. Portable: equipment can be taken to the field, making it ideal for in-service inspections of large structures that can't be moved to a testing facility. Of course, no method is perfect. Let's be honest about MPI's limitations. Material restrictions: this is the big one, it only works on ferromagnetic materials. Aluminum, copper, titanium, stainless steel, and other non-magnetic materials? You'll need a different method like dye penetrant or eddy current testing. Depth limitations: the method only detects surface and near-to-surface defects. For deep subsurface defects, you'd need ultrasonic testing or radiography. Orientation sensitivity: defects must be roughly perpendicular to the magnetic field to be detected. This means parts often need to be magnetized in multiple directions, which takes time. Demagnetization requirements: once MPT has been completed, the component must be demagnetized, which can sometimes be difficult. Residual magnetism can interfere with machining, welding, or electronic components. Environmental factors: extreme temperatures or high humidity can affect the performance of mount. Particles may not adhere properly in very humid conditions. Post-inspection cleaning: parts usually need thorough cleaning after inspection to remove all particle residue, especially if they're going into service in sensitive applications. Finding a defect is one thing, deciding whether it's acceptable or not is another skill entirely. Inspection results must be evaluated against established acceptance criteria. These standards vary by industry and application. For example, aerospace components typically have very strict acceptance criteria, even tiny defects may be rejectable. In structural steel, some level of minor indications might be acceptable. Common standards include ASTM A1444 for magnetic particle testing, AWSD 1.1 for structural welding, and ASME boiler and pressure vessel code section 5 for pressure equipment. Inspectors must be trained to distinguish between relevant indications, actual defects that need evaluation, non-relevant indications, particle accumulations caused by surface conditions like scratches, but not actual defects, false indications, particle patterns that look like defects but aren't, such as from writing on the surface. This is where certified NDT technicians earn their keep. Proper interpretation requires understanding the theory, principles, and applications of the method. Certification levels range from Level 1, performs inspections, to Level 3, establishes procedures and interprets codes. Let me share a real-world example that shows why MPI matters. In aerospace applications, companies use MT coupled with other methods to ensure that components of landing gear are free from defects, thereby guaranteeing the highest levels of safety and performance for aircraft. Imagine a landing gear component with a tiny fatigue crack just 0.5 mm long. To the naked eye, it's completely invisible. But under the stress of repeated takeoffs and landings, that crack will grow. If left undetected, it could eventually lead to catastrophic failure. Using magnetic particle inspection with fluorescent wet method, an inspector magnetizes the component, applies the particle bath, and examines it under UV light. That tiny crack glows brilliantly green, clearly visible. The component is removed from service, the cracked part is replaced, and a potential disaster is avoided. This same scenario plays out thousands of times daily across industries worldwide. Crankshafts in your car, welds on bridges, pressure vessels in refineries. MPI is quietly working behind the scenes to keep us safe. So there you have it, a complete deep dive into magnetic particle inspection. We've covered the science of magnetism, the inspection process, equipment and materials, advantages and limitations, and real-world applications. MPI is one of the most widely utilized non-destructive testing methods, and for good reason. It's fast, effective, and cost-efficient. Whether you are considering a career in NDT, working in manufacturing or quality control, or just curious about how we ensure safety in critical industries, understanding MPI gives you insight into the invisible world of defect detection. If you found this video helpful, please give it a thumbs up and subscribe for more content on NDT methods, industrial technology, and engineering topics. Drop a comment below what NDT method should we cover next. Ultrasonic testing, radiography, let me know. And remember, the next time you board an airplane or drive across a bridge, there's a good chance magnetic particle inspection played a role in keeping you safe. Thanks for watching, and I'll see you in the next video.